welcome back.
Hi.
Hi, good afternoon. You doing all right?
Yeah. Yes.
Woo! Had to get the lollipop out of the mouth. All right, so today make sure you've got your favorite superhero with you on your desk. We're going to be doing some very light calculations today. You'll also need your protractor with a ruler on the straight edge. So again, another reminder, if your protractor does not have this ruler on the bottom, please go get one. You'll need two different color writing utensils today, your main color and then another color. We're only going to do a little bit of color coding. They're not going to be super specific and they don't have to match mine. Okay? They just need to be a color that's different from what you're writing the main part of your notes in, okay? All right, let's go ahead and get these cut out and ready to go. Date and title is bigger than it has been. I made the date and the title a little larger this time. I was looking back into my table of contents on Friday, just flipping through my notebooks and realizing, these are really small and hard to read. So I've made them a little bigger if you cut them out and use them, so hopefully they'll be a little easier for you to read. If you don't use them, someone else might. And then the thing to note about this particular graphic is the dot needs to stay with the line segment. So don't cut these apart. They're best friends. So leave them all together.
How was your Halloween?
My Halloween was really good, thank you. My LARP group's carnival was really good.
Your what?
My LARP group, my live action role playing group. Yeah, my nerd is showing again. It was a lot of fun. We had a number of people show up, so that's good. Hopefully with a bit more advertising and more stuff on Facebook, next year's might be a little bigger, a little better.
Yeah, like when we did, our family got together,
Uh-huh.
and we gave out candy, but you guys could also play games. And
Okay.
you guys would win fishes.
Fishes?
So, yeah, so they took home fishes. It was like an activity thingy.
Oh, that's cool.
Whoever comes to get candy, they can play the game if you want to.
That's really neat. This particular graph, the one that's blank, we'll use it another day. I just have it in here because I knew we would need one. So go ahead and set it into your baggie. Once it's trimmed, you're not going to use it today. Notice the line segment and dot I've trimmed a little bit. You're welcome to do that as well. Yes, your spiral's over here. It's the yellow one, right? You're welcome.
So is this the work we're going to do for this section, or is it going to go into this 6 weeks?
Only one item from this is going to go into this 6 weeks, and it'll be a really short notebook, one problem kind of thing. You did it, here's your 100. You didn't do it, I'm sorry, here's your 69. All right, and then I trimmed the hexagon a little bit so that it looks something like this. All right, so you have your hexagon. You have your rectangle in the coordinate plane. You have your line segment and dot. And then the date and title. So let's go ahead and get started. I'm going to update my table of contents first. Today's going to take 2 to 3. I clearly need to do some work in my table of contents. I'm missing a lot of page numbers. I'm almost done with one whole page too in my table of contents. All right, so last week we left off with rotations, the last of our isometric transformations. And we took several pages to look at rotations, and we finished it off with a quick notebook check to make sure that y'all could do an algebraic or constructed rotation. There was a homework assignment for this, so make sure you leave a place for that KWL for that particular assignment. And you'll start your notes for today on the very next page. Chapter 9, Lesson 6, Dilations. As always, title and objectives listed under the La Feria logo. Today is Monday, November 2nd. It's my dad's birthday, depending on how we're feeling, because sometimes his birthday is on November 2nd, other times it's October 2nd. He was born in Mexico. And in Mexico, you have a certain amount of time in order to register the birth. It doesn't happen immediately. You have to do it. And my granddad kind of missed the due date to get that turned in. And so in order to prevent the fines that he'd have to pay for missing the due date to report in for October 2nd, he said that my dad's birthday was November 2nd.
He has 2 birthdays.
So he's got 2 birthdays some year. Other years he has no birthdays. Because October 2nd will come around, he's like, it's my birthday. And we're like, no, it's not. Your birthday's November 2nd. He's like, oh. And so he'll wait a month and go, hey, it's my birthday. And we're like, no, it isn't. Your birthday was October 2nd. He's like,
man,
oh.
that's really
We all laugh. And then we give him cake, and he's happy. All right. My abbreviations, my abbreviated objectives. All right, let's go ahead and get started. I want to start today's conversation with a quick recall moment. What is a transformation? Yeah, it's some sort of change that we're applying. Since we're in geometry, we're applying this change on shapes. So we're going to be moving triangles and squares and rectangles and all sorts of things. Last week when we were looking at rotations, we noted that that was the last of the isometric transformations that we would be studying in this section. And so I would like to start off our first new topic with non-isometric transformation. What do you think this is?
no change.
No change? What did isometric mean? Isometric was it didn't change the shape and it didn't change the size. So what does non-isometric mean?
The shape and size.
But it does change.
It does change the shape and size. So we'll put does not preserve congruence. And hopefully I can spell the word preserve right today. Does not preserve congruence. And so shorthand, size and shape changes. There's a non-isometric transformation out there that takes a donut and turns it into a coffee mug. Yeah, that's what I did. Like exactly that head motion. It was the exact head motion I did when my college geometry professor said that. And then he took Play-Doh and he showed it to me. I went, whoa. And then he proceeded to show all the algebraic numbers behind it, and I was like, I can't, what? What does that squiggle even mean? And he was like, well, take this class. And I was like, I graduate already, I'm sorry. So I never took that class. So I don't know how you actually turn a donut into a coffee mug, but I've seen the computer models and animations on YouTube. They're really cool. I'll try to find one and put it in the description below. All right, so non-isometric transformation. You can do stuff like take a donut and turn it into a coffee mug. We won't be doing that in this class, obviously, because I don't understand how to do it. But what we will be doing in this class is we will be doing similarity transformations. And similarity transformations are changes, but these are proportional changes. What this means is if I have a box and I'm going to change it proportionally, I'm going to make, like, say, one side, like 10 times bigger than its original. Then all the other sides also have to be 10 times bigger than their original size. Okay? The similarity transformation that we will be studying in particular, because I believe there's more than one kind. I don't know, Google it, double check. Let me know. But the one that we're going to be studying and doing is the dilation. So the dilation is a similarity transformation. And all it's going to do is change the size of things. And it does that with respect to a single fixed point. We'll talk about what that point is in a second. Dilation has two aspects, two ways you can dilate. You can dilate either as an enlargement, means we're going to make the thing bigger.
The paper fell.
Huh?
The paper
Or it can be a reduction. Which is to make smaller. So when we're talking dilation, we're talking, hey, we're going to do an enlargement, which means the figure that we're going to end up with is going to be the same shape, but it's going to be larger than the original. Or we're going to talk about a reduction, meaning that while we have the same shape, it's going to be smaller than what we started with.
Like those, when they, the 3D building, and then they make it bigger?
Yeah, exactly. That would be a dilation. They do what's called a scale model. They make a really small version of the building that they want to build, and they use that to help them project it into the real world sizes. Yeah, it's exactly what they're doing. They're doing an enlargement dilation.
That's kind of hard to make, like the CAD files for 3D models and stuff.
Oh yeah, the 3D CAD. I have.
I have it on my computer. It's like really confusing.
Whoa.
It's like sometimes you're looking at it, you make it, it's like, oh, I made a rectangle. You turn to the side, it's like,
It's like all weird.
yeah, it's like.
It's like, not a rectangle. Gotta try again. I may need to sit down with you and have you teach me CAD because I've never played with that. I'll let you know once I get that program in. I had said that this dilation happens in respect to a fixed point, and that fixed point is called the center of dilation. This is the fixed point from which the dilation occurs. Is anyone in here taking art?
Last year.
You took it last year, you're doing it now. Okay. And I know I saw Melanie's project on this one. You're doing the perspective drawings right now, right? What's that dot called that all your lines have to go toward? To make your perspective. Huh? Point of origin? I think you're in the right spot.
Perspective point?
Your perspective point, it can be called that. I think more typically what this point is called is it's called the vanishing point. So in art, the point that all your perspective lines are going toward that seem to vanish away into the horizon, called the vanishing point. Here in math, that point is called the center of dilation. Because as you're moving away, things are getting smaller, and so they are undergoing a reduction as it goes away. Okay? So you're welcome to call it either center of dilation or vanishing point in terms of just kind of general conversation in this class. But you'll see it in homework, directions, or tests or quizzes and things like that as center of dilation. The other thing that you need to think about when you're talking about dilations is the scale factor. And I believe in that art assignment, you were just said, like, here's the vanishing points and just make it go toward that. And you're like, okay, but how far? Right? Not really? You're just like, I'm going to go that far and I'm happy with it? Okay, well, good. Some people freaked. I know when I had to do it, I freaked out because I was like, well, how far do I go? And I got told, well, however far you want. And for me, in junior high school, when I was doing this, that really messed with my head. So if that messed with your head, this scale factor is what's going to save you, because this is the number. How did I write this the first time? Okay. The number by which the dilation occurs. So this number is going to kind of control how far you're moving to or from your center of dilation. Okay. Questions on all the vocabulary today? There was quite a bit. All right, no? All right, let's go ahead and set up for our first example. You'll want to glue in the one with the dot and the line segment, like that. And here are your directions. The directions are: draw the dilation of line segment AB by scale factor 0.5. That could also be written as 1/2. So you might see it written either way. Take the rest of your workspace and divide it into 2 by folding it. We're going to be writing the directions, how you draw this translation on the right. We'll be doing our actual work on the left. Did y'all get the directions written down? Not quite yet. See a few people still writing. Draw the dilation of line segment AB by scale factor 1/2, 0.5. All right, here are the 4 directions. I'll give you the 4 steps and then we'll do the dilation. Step number 1. Draw segments from each point of the pre-image there's only 2, A and B, to the center of dilation. In this case, our center of dilation is S. Step number 2. Measure these segments. And literally you will grab a ruler and measure them. You're not going to run distance formula. You're not going to break out the compass and try to figure this out. No, you just grab the ruler and measure them. Tell me how many centimeters, inches, feet, yards, whatever you're given. Okay? Number 3. Multiply these measurements by the scale factor. Then mark the new measurements. Those are our 4 steps. All right, let's do it. Step number 1, drawing segments. I'm going to grab my straight edge protractor.
It's supposed to be doing in pencil, right?
You're welcome to do it in pencil. I need to do it in ink because pencil doesn't show up very well. Yeah, but yes, best to do it in pencil just in case. All right. So point S is a really kind of large mamma jamma dot. So just pick a spot somewhere in there and say that's where S is going to be, and make sure that all your lines connect to that particular location. I went ham with the enlargement here. Okay, so there's A to that point, and here's B to that same point. There it is. I'm going to measure them, and I'm going to write my measurements over here. So SB and SA. So I'm going to measure these in centimeters. And I'm measuring them in centimeters because centimeters are going to be easier for me to find the decimal points of
It's 4.5.
yeah. It's going to be easier for me to find the decimal points. Whereas if I did this in inches, I'd end up with something maybe like 2 5/16 inch, and then I'd have to translate 5/16 into a decimal, and then, no, way too much headache. 4.5 centimeters. Do the same thing for the other line segments. On mine, I end up with,
Bigger.
yeah, a little bit bigger, 4.8.
Yeah.
You may end up with a number different than mine. It just depends on where you connected them over here in S. One class period, they were both the same at 4.5. So it depends on where you put it. All right, that was step number 2. Step number 3 is multiply these by the scale factor. And here's what it's going to look like. S to B prime is going to be given by the scale factor times the length of my original segment, SB. Because I am moving point B some distance relation to point S. Help me out. 0.5 times 4.5?
2.25.
2.25. Your hero gave you that, yeah?
Mm-hmm.
Who is your hero?
Carol Danvers?
Carol Danvers. Do we know who Carol Danvers is?
No.
No?
Is he a guy?
No, that's a girl. Flip her over. Flip her over.
Mrs. Marvell.
Miss Marvel.
Oh.
Oddly enough, she's a DC character. I think. No. This Miss Marvel.
She's a Marvel.
This Miss Marvel's a Marvel character. She's with Captain America. You're right. I'm thinking of Captain Marvel. Huh?
Isn't it his sister, Miss Marvel, in the DC version?
Yeah, in the DC version, it's his sister, Billy Batson's. It's confusing. Anyway, 0.5 times 4.8.
2.4.
2.4.
Miss Marvel.
Miss Marvel helps out. And then I heard from you. Who's your hero?
Deadpool.
Deadpool.
Is he a guy?
Yeah, that's the guy.
He's a boyfriend.
He's your boyfriend? All right. Step number 4, mark the new measurements. Okay, S to B prime is 2.25 centimeters from S. So I'm going to measure. I'm going to put my 0 on S. And I'm going to go 1, 2, and 2.5 is right around there. So B prime is right there where those two things intersect. I'm going to do the same thing for A prime. So line up my S with my 0. And I'm going to go 1, 2, and 0.4. So this is where A prime is going to end up. Last but not least, take your protractor straight edge and connect the dots. There it is. I have drawn the dilation of line segment AB by a scale factor of 0.5. Cool? All right. I'm out of room on this page, so join me on the next one. Get it set up. One more page of notes. Can I turn the page? Glue in the picture of the rectangle on the coordinate plane. That is the figure that we'll be working with for this part. So your notes look something like this. And we're going to set this up as our next example, but we're going to title our example rather than give it the directions. And the title of this example is Dilation on the Coordinate Plane. In particular, this dilation happens centered at 0, 0, the origin. Transformation centered at 0, 0, the easiest algebraically to handle. They require the least amount of kind of fussing in variables. So that's why we always start with them. Algebraically, what needs to happen when you do a dilation on the coordinate plane centered at 0, 0 is this. This is where the other color comes into play. You're going to take your coordinates x, y, and you're going to map them. You're going to move them. You're going to transform them this way. Take some number a, multiply it by the x coordinate, and then take that same number, which we're calling a, and multiply it to the y coordinate. That's it. You're done. That's it. But I need to tell you what that number a is. This number a is representing the scale factor. While you finish writing this down, I'll get the examples directions off to the right. Still see a few people writing, so I'll wait.
This one be the notebook check?
No, the next one will be. All right. So the directions on this state, draw the dilation of rectangle ABCD, centered at 0, 0, so here's your center of dilation, by A equals 1.1. Now notice there isn't a unit of measurement here. This isn't 1.1 centimeters. This is some value that you're multiplying two distances in order to figure out where you're going. All right, the algebra notation tells me just to take this number and multiply it to each coordinate of my point. And then the new number I get for each coordinate, that's where the point is going to end up. So I'm going to do that here, down here at the bottom. So A prime is going to end up at A, which is my scale factor, times the x coordinate of point A, comma, the scale factor A times the y coordinate of point A.
The A at the end.
There is a little a at the end. Notice how it's a capital A, not a lowercase a, because I'm saying the name of that point. So this is the x-coordinate of point A, and this is the y-coordinate of point A. Okay, I'm going to fill in what I know. This little a here, scale factor is 1.1 times the x-coordinate of point A is, according to my diagram, 2. A scale factor 1.1, and the y-coordinate of point A is 4.
Oh yeah, 4.
All right, I'm going to need the, what's it called? Calculation help, 1.1 times 2? 2.2?
Yeah.
All right, and 1.1 times 4?
4.4.
Awesome. Repeat this for every point in your figure. Do that now. You do not have to write out all of the things that I'm writing out. You write out just what you need in order to show that, yes, I know what the scale factor is, and yes, I know that I need to multiply. I'm going to write them all out because as the teacher notebook, it's got to be super clear where all the information is coming from.
It's just the opposite for B.
Yeah. Oops. My brain went on autopilot there. All right, make sure I got the right numbers in the right spot. Did I?
8.8. Yes, you got it right.
All right, let's go graph it.
Ooh, it's gonna be hard.
Yeah, because I don't have decimal points on this one, you're going to have to kind of guesstimate. So yours isn't going to be the exact same place as mine, but as long as you're close, we'll count it as good. So 2.2 and 4.4, there's A prime. 4.4 and 2.2, there's B prime. Oops, I have that in the wrong spot. Should be here. C is going to be 8, 8,
Burn.
6, 6, and D should be 6, 6, 8, 8. And then as always, take your straight edge. And trace the lines.
They're like right next to each other though.
They are, because we didn't move it really far, did we?
No.
Look at how close to 1 this number is. So what do you think a scale factor of 1 is going to do? Yeah, absolutely nothing. What do you think a scale factor of 0 might do?
Zero. It's gonna be 0, isn't it?
Yeah, all points go to 0, which
Yeah.
means we end up on our vanishing point and the thing disappears. Very nice. So does your figure look something sort of like this one?
One of the games.
You're almost done? Okay. The next page, go ahead and title it Notebook Check 6. Let me know when you're ready for me to move off of this page.
Wait, notebook
Right.
what?
Check 6.
Can you show me the because I didn't get it?
D? Sure. There? Okay.
The other half of the page is for the next one, or what?
Yeah, the other page is for next one. Yeah. So if you've, I'm going to put it on a brand new sheet of paper because mine's not going to fit. If you've got half the page or more available, you can probably just continue on. And I say probably because you get to pick something, and depending on what you pick, you may not have room. So,
How many lines do you think we'll need?
again, that depends on what you pick. At the very least, you're going to need as much room as this, and then the directions, which is 1 line. So bare minimum, you're going to need this plus 1 line. But depending on what you pick, you may need way more space than that. Can you guess what your notebook check is?
Instruction.
Yeah, a dilation construction. Notebook check 6 says dilate hexagon MPRVWS. Okay, that one.
So we're gonna do what we did
On the first one. By A equals, you tell me. I'm going to put restrictions. You may not pick 1, and you may not pick 0. Because as you said, 1 doesn't do anything, and 0 turns it all into a dot. Okay? So any other number is totally okay. So now, take a moment, look at the space that you are reserving out for this, and say to yourself, self, I want to use a scale factor of 27. I don't know, I made up a number. Am I going to have room?
Yeah.
If you're not, either move your thing around so you think you will, or else pick a different number.
0.5?
0.5 is okay. 0.1 is okay. 0.00000001, probably not. It's going to be too small.
What's 0.5?
0.5 is okay. 0.2 is okay. 3 is fine. 0.3 is fine. I'm worried once you get beyond, say, a scale factor of 3, it just might get too large for your paper. Okay? Once you've decided what your scale factor is and where you think is the best placement for your thing, go ahead and place it down, glue it in, and then begin your construction. You have the rest of the class period to do this. That's about 10 minutes.
How would you combine them all together?
What do you mean combine them all together?
Oh, it's gonna become another
Hexagon.
little hexagon.
Yeah.
Okay.
Remember that the shape stays the same. You've just got a different size hexagon.
Can you zoom it in?
I will be happy to.
And like,
Like,
Sure.
It's different